So last lecture we were looking at the Markov decision process, right? So this is like an encapsulation of all the things that we have been looking at. So states, actions, transition probabilities and rewards, and your goal is to learn to mapping from states to actions, right? So that you can maximize the total expected reward. So we'll make this a little bit more formal as we go along. And the goal of the agent is to learn an optimal policy, which is a policy that achieves this maximum total expected reward. So that's where we are at, right? So if you remember, I talked about specific conditions on the state space, that you should have a finite set of states, a finite set of actions, right? And discrete states and discrete actions for the time being, right? And then you have either you could model it as a joint distribution. Right, either you could model the dynamics as a joint distribution, right? Joint distribution of both states and rewards, right? Given the current state and the current action, what is the probability distribution over the next state and the reward? Alternatively, you could also think of it as two components, right? So there are two components, P and R, where P talks about the probability of transition of states, right? And R talks about the expected reward, and where the expectation comes from an expression like this, right? And then the goal is to learn this policy, and the policy can be deterministic or the policy can be stochastic, right? So if it is deterministic, so it's either pi of a given s or pi of s comma a, right? I could use one of those two notations, and if it is deterministic, then I typically use pi of s equal to a or a1, right? Depending on what action I'm taking. So when I talk about taking a reinforcement learning problem, right, and formulating it as an MDP, typically the things that I have to think about, right, when I'm trying to design a reinforcement learning solution, things that I have to think about are, okay, so what are states? Right? So states should have enough information so that I can make decisions, right? If you remember, we talked about states having a Markov property. So what does that mean? It means that the state has enough information so that I can predict what the next state is going to be, right, without having to know more history of how I came to that particular state, right? So state has enough information so that I can predict what will happen going forward without knowing any more history. So that is basically what we mean by a state needing to have enough information to take decisions. So frequently, this means that we can't just take the raw sensations of the agent, right, or raw sensations that are coming in, and use that as the state. Right? So what do we mean by raw sensation? It's like you can think of it like looking at the tic-tac-toe board, right? Just see where are the current pieces that you have already played, right, or looking at a chessboard and looking at where the current pieces are, and then using that to make your decisions. Right? So quite often that is enough, but sometimes it is not. Why? Because if you knew what were the last 3 moves your opponent made in a chess game, you might be able to predict better as to, okay, this person is having this strategy in their mind, and therefore they are going to play like this next time. They are going to move this pawn next time rather than move the bishop, right? But if I just have a single snapshot of the board, I might not be able to make these kinds of refinements about the predictions based on what I think is the opponent doing, right? Likewise, if you are thinking about, say, a robot, right? A robot that has multiple sensors on board, like sonars and depth sensors and things like that. So given a particular location, a robot might not be able to exactly know where it is, right? But if you knew some history of like 10-15 steps that the robot has taken, then you'll know exactly where the robot is in the space, and you'll know you can make the right decisions, right? So this is what we mean by saying raw inputs are often not sufficient, and you will have to look at some kind of processing of it. And as we go along, we will talk about it. But at the end of the day, once you have done the modeling, we assume that the state based on which you take the decision has enough information. The state itself could be instantaneous inputs like the board positions, or it could be some kind of a history of inputs and so on and so forth. But for most parts of the discussions that we will have, we will assume that the state is well defined, and you can continue acting as if you have access to the Markov state, right? So later on, right, towards the end, we'll talk about situations where you don't have Markov information, or you don't have enough information about the state, and how you do to fix it, right? The second thing that you have to decide is actions, right? So the actions are literally the control variables that you'll have to take, right? So the actions are the control variables. So it could be the moves in a game, right? So tic-tac-toe we talked about. So there are 9 possible moves that I can make to begin with, and slowly that keeps coming down as I keep playing the game. But these are basically a discrete set of moves, and I know about those, right? Or it could be like items to recommend. We talked about recommendation system, right? So the items to recommend could be the action. So I have these nice discrete actions. Or it could be continuous, right? So continuous actions could be like I have a robot that I'm controlling, right, or a car that I'm driving. It could be some kind of a torque that I give to the motor, or the pressure with which I push a pedal, right? So all of these could be actions, in which case they are continuous actions. And so for the modeling part, we treat them as continuous actions. But then when we actually come up with algorithms, we might actually go back and discretize. So I might say, okay, there is this angle at which I'll have to turn it. So it's a continuous value between 0 and 360. But what I will do is I look at it at increment of 5 degrees, right? So that basically makes the number of actions much smaller, right? So those kinds of things I could do further processing, but these are typically, you have discrete actions or you have continuous actions, right? So it's not as simple a question as it might seem at first. When you're talking about games, it's all easy, okay? Let's talk about the question of driving, right? So what are the actions when you are driving? Think about how you would do. If you would drive a motorcycle or you would drive a car, right? So you could turn the steering wheel, right? You could turn the steering wheel to some angle, right? So you could say that what is the angle that I'm going to turn the steering wheel to, and what is the acceleration that I'm going to give, right? How much I'm going to push the pedal by, right? So those could be the actions that I'm taking while I'm driving. On the other hand, you also have another level at which you are making decisions. What is that level? You have to say, okay, I'm going to turn left here, I'm going to turn right, I'm going to go straight, I'm going to turn at a 45-degree angle into the other road, right? I'm going to go fast, I'm going to go slow. So those are the kinds of decisions that you make. And then turning left or turning right would then get translated into some amount of rotations on the steering wheel, right? Or some going fast or going slow would translate to pressing the accelerator or pressing the brake, and with certain amount of pressure and so on and so forth, right? So sometimes you just think at that higher level of planning, right? You don't worry about actions that involve like this continuous control of the steering wheel or the pedals, but more discrete things like go left, go right. Sometimes that's easy for us to think about, and that is the level at which we have these actions. And again, sometimes you could even go lower. If you think about it, pressing the pedal requires you to move your muscles. Turning the steering wheel requires you to move your muscles, right? So you could think of it in terms of muscle movement. So what should I do to make sure that my leg presses down? What should I do to make sure that my hand pulls up like this, right? So that it holds the steering wheel and turns it, right? Now that's a level that we rarely think about, because as kids, right, we have actually done this many times. We kind of understand, okay, there is some dynamics to how my leg moves, there is some dynamics to how my hand moves, and I have kind of internalized all these actions, right? So I don't even think about them anymore. So now the question that I have to ask you is, when you are driving a car, right, at what level are you making these decisions? It turns out you are making these decisions at all levels simultaneously. So humans are so good at going up and down this kind of a hierarchy of actions, right? So sometimes you think of, sometimes you act in the space of muscle control. Sometimes you act in the space of these continuous directions, and sometimes you act in the space of discrete decision variables. And in fact, at other times you act in the in a much larger space. Hey, I want to go to Bangalore, right? As opposed to turn left, turn right, and so on and so forth. So sometimes you plan at a much more abstract level when you are trying to learn how to control a system. Right? So it's designing an RL solution is not as straightforward as just coming up with some states and actions, right? And you have to think about it a little bit, figure out what is the actual granularity at which you want to learn, right? And once you decide what your actions are, you might have to also have to fiddle around with what the states that you are using. So towards the end, right, we look at one module where we talk about actually having this kind of multiple granularities of decision making. But for the time being, we're just going to assume there's a single granularity, and somehow the designer has come up with it and gives you a set of discrete actions that you are going to use. Okay, but when you try to make real problems into RL solutions, then you will have to think about what should be the states and what should be the actions. Right? In many of the cases that we will give you examples, we will give you exercises where you are supposed to do this, right? Take a word problem and convert that into a RL problem, where it will be more or less straightforward, right? We are not going to pain you too much in the assignments in the course, but it's something that you have to keep in mind when you are actually doing the real problem solving. Right? So finally, the third component of designing an RL solution is basically the reward function. Right? So the reward function should be something that tries to define the goal of the problem, right? Not something that tries to tell the agent how to solve it. Right? Sometimes what happens is you might be giving the wrong signal to the agent, right? To the RL agent that is interacting with the environment, right? So you might be giving the wrong signals to the agent if you give wrong rewards. So I'll give you some examples in the next few slides, but typically, you'll give rewards like, okay, I'll give you a reward of +5 if you get to the goal, like wherever I want you to go. You want to go to Bangalore, you'll get a reward of +100 when you reach Bangalore. And if you run into a truck on the way, you will get a reward of -1000, right? Something like that, right? But then again, you have to be very careful. So there was this example. So where there was this student who was trying to design a reward function for an RL agent learning to cycle. She heard about people saying, "Oh, RL is just like cycling." So that's what the example that you keep giving. So she said, "Okay, I'm going to actually get an RL agent to learn how to cycle." And so she set up the very, very detailed cycling simulator, right? And then she set up a center point in a blank space, right? She said, okay, the simulator says that there is a goal somewhere in the middle, right? And then the cycle starts somewhere here, and the goal is for you to balance the cycle, right? And then drive until you reach the goal, right? Ride the cycle until you reach the goal. So what was happening was that the reward was very, very sparse, right? So you have to start here. First you have to learn how to balance the cycle. And it is not enough if you go like this, you have to learn to go in a particular direction to reach the goal. So then she thought, okay, this is taking too long, therefore no learning is happening, it is not learning to find a reward. So I'm going to give it a small reward whenever there is a component of the velocity in the direction of the goal. And there's some component of the velocity in the direction of the goal. So I'll give it some positive reward. So whenever there is a component of velocity in the direction of the goal, I'll give it some small reward, say 0.1. And when the agent reaches the goal, I'll give it a high reward, say 10. Then she set up. Then again she found that the agent was not learning to go to the goal, but interestingly, the agent learned to cycle. So what did it do? It went around in a circle. So what happens is, half the times when it's going around in the circle, it has a component of velocity in the direction of the goal, right? So it just kept accumulating rewards as it kept moving towards the goal, right? But then after some time it will go away and then it will come back. So what was happening was, it is trying to get the maximum total reward, right? So it is basically adding up all these 0.1s and it was getting more than the 10, which it would have gotten if it had gone to the goal directly, and then it would have stopped, right? Instead of getting a 10, finite 10 and stopping, it decided to get an infinite number of 0.1s and kept riding in the circle. So sometimes we try to design reward functions that help the agents to learn, and then that ends up becoming a really a bad choice. Okay, so we have to be very careful when we are trying to design all of these things. So having said that, I mean, I'm giving too many caveats right up front, right? So you might start thinking, hey, what is this? Do we actually learn anything using reinforcement learning? But remember, we saw a lot of success stories of RL, right? So there are a lot of guidelines from the literature and use cases and other things for you to draw upon when you want to decide these states, actions, and rewards, right? So it's fine. So don't worry about it. And typically, reinforcement learning, right? So reinforcement learning talks about solving problems where I don't have the knowledge about the full system. So reinforcement learning talks about solving problems when I don't have knowledge about the full system. That means that I don't need to know the P and the R, right? Or the R maybe. I don't need to know the P, right? I just need to know the states and the actions, and I should be able to solve the problem by kind of interacting with the system. That's what we we have, right? So the RL system, the main thing that we have is that it works with close interaction in the system and tries to learn. And the idea is that without knowing about the P of the system, I should be able to learn, right? So even though we are talking about a Markov model, it's an ideal case, right? So you might not know the model itself. All you are able to do is get this kind of interaction going. You remember state, action, next state, reward, state, action, next state, reward, that continuous stream of experience that you get, right? That episodes that you get while interacting with the environment, that is what you're going to learn from. So when you're designing the solution, you don't really worry about the P, you just think about the S, A and R. Okay. So here is a simple example. Let's say that you have a robot, right, that is trying to navigate in a 2D workspace, right? So basically there is a square workspace, and the robot is trying to get to the state mark G. Okay. What is happening is when the robot is moving around, there are multiple obstacles. That could be chairs and tables and bookshelves and whatever that are there in the space, and therefore you can't actually, the robot can't occupy the same place as these obstacles. So you can't enter these cells, right? So what people do is, okay, instead of looking at it as a continuous space, remember we can't operate, right now we are assuming the states are discrete, right, and finite. So what people do is they draw a grid, right, on the continuous space. They draw a grid on the continuous space and then assume that the robot occupies a grid cell, and then it moves from one grid cell to another, right. It moves from one grid cell to another, and if some part of the grid that you have drawn has an obstacle in it, you just basically shade the entire grid and say that, hey, you can't move into this obstacle. So all the white cells here, right, are grid cells in which the robot can move, and all the gray cells are grid cells which have obstacles and the robot can't move, and you get a reward of, and the goal is to reach to the state mark G, right. When you think of it as an MDP, then you have your states, which is which grid cell you are in, right, which cell you are in is your state, right, and you have your set of actions. So your set of actions could be, move in the cardinal directions, right. So when I say this, right, so set of actions could be, okay, move north, right, or move east, or move west, or move south, right. Or you could also expand it, right, you could have 8 actions, right. So you could move northwest, you could try to move northeast here, you could move southeast, and you could go to southwest also, right. So whenever you try to move somewhere and you get into an obstacle, then basically that move doesn't happen, you stay where you are. Okay. So there are different variations of this problem where you have only 4 actions versus where you have 8 actions. So quite often we'll look at the 4 action version of it. Okay. Now, so we have the states, we have the actions, and what about the P, right? We already told you about the P. So you have 4 actions. So if you try to move north, if the cell above you is free, then you can move north, right? If you try to move south, if the cell below you is free, you will move south, likewise, right? You try to move northwest, if the cell here is free, you can move. So if you are in this particular state, then all the north actions don't work, but you can have west, east and south, right? If you are in this state, then you can't move west or north, you can only move east or southeast, right? So like that, right? So that's basically your P is done. So what about your R? Right. So R depends on what you are trying to solve here, right? So your goal is to reach the state mark G. Then what you can do is you can give yourself a reward of say plus 10 on reaching G and 0 everywhere else, right? And you are trying to maximize the total reward, remember that, right? So what will happen is, if you do this, right, reward of plus 10 on reaching Z and 0 everywhere else, right? So whatever you do, right? So if you go here, it's 0, you go here, it is 0, but if you go here, you get a plus 10, right? So if you say that that's the condition, so I can go any which way I want, right? I can go like this, right? That's also fine. Or I can go like this, or both will get a reward of plus 10, right? Both those trajectories will get a reward of plus 10, but so is that my goal? If that is only my goal, then it is fine. As long as you reach the end point, I am happy, right? But then I can take arbitrarily long to reach my end point, because I could do something like this. Oops. I could do something like this, right? So that will also reach my end point. I'll still get a reward of 10, right? But that's somehow seems to be not the right thing to do, right? So we would like to have some mechanism by which we can control this. So one way of doing this is to say that, hey, you might get a plus 10 on reaching the goal, but along the way, every action you take, right, is going to give you a minus 1. Right? Every action you take is going to give you a minus 1. Now, what does it mean? So if I go like this, right? So I am going to take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 minus 1s, right? Minus 14, right? Before I reach there. But on the other hand, if I decide to do this, right? So that will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? I'll basically get only 10 minus 1. So it's basically this one gives me minus 10 plus 10, 0. This one gives me minus 14 plus 10, which is minus 4. So obviously this trajectory, which seems to be a more straight path to the goal, is more rewarding than a slightly circuitous trajectory, and therefore I would prefer to do this, right? What's more interesting is, if I am going to do this, I actually don't need my plus 10 even, right? So whether it is minus 10 versus minus 14, it's all fine as long as I reach the goal, right? And I do it in the least number of steps. I'm happy with that. So that is one way of controlling for how you would get there, right? So that's R, right? So states is which cell you are in after you put a grid on the continuous world. Actions are one of these 4 or one of these 8 actions. P is the natural transition as given by the directions of the action. And R is minus 1 in every time step until you reach the goal, right? So that's basically a well-defined MDP that allows you to solve the shortest path problem to reach the goal from anywhere in the world. So next, we will look at another example of an MDP, right? So it's a little wordy because it's a word problem. So I'm going to walk you through this word problem, right? So so that is a computer manufacturing company, okay, and it sells a product. Right? So the product can either be a hot selling product, right, very popular product like an iPhone, or it could be a poorly selling product which no one wants to buy, right? Now, if the product is hot selling, right, the company can either advertise its product, right, or not advertise the product. Right? So if it advertises the product, it's going to incur some expense, right? But it's also, because it's a hot selling product, it's going to get some income. It's also going to have some expense because it's spending it on advertising, right? So we are going to say the overall income is, say, 4 units, whatever it is, right? And if you advertise, then the product continues to be hot selling, right, with a probability of 0.8. So with a very high probability, it continues to be a hot product, right? However, with some small probability, 0.2, the product starts selling poorly. Okay. Then the company can alternatively say that I'm not going to advertise. That means I'm not spending any money. I'm a hot product. I'm going to keep getting income, but I'm not spending any money, right? So I have a lot more income. So I have 6 units of income, right? But the problem is, because I'm not advertising, that's a greater chance that the product will become a poor selling product from a hot selling product. So only with 0.5 probability, it will continue to be hot. Okay. Now, if the product is selling poorly, right? So the company, so you don't want to just advertise a bad product, right? Even though many people keep doing it, but you would like to improve the product. See? So what you can do is, you can either perform some research to improve the product, or not perform research and just hope that the product, becomes hot somehow, right? So this results in immediate reward of -5 if you do research, because you have to spend on doing research, and it is poorly selling, and you're not getting enough return, right? So that's a problem. But if you do research, even though you're spending money, with the probability of 0.7, you'll now become a hot product, right? So now you'll become a hot product, and therefore you'll start making more money if you do research. On the other hand, if you don't do research and just stay, right, just let things go as it is, right, it will get a reward of -3 because it's not doing well, so you're getting penalized for that. It's not doing well, so you get only a reward of -3, right? But you'll continue to remain a poor product with a very high probability, in this case 0.6, okay? So I've given you a lot of numbers, a lot of actions and things like that. Let's see how we can formulate this as a Markov decision process. Right? So what are the what are the states, actions and rewards, right? That's and the transition probabilities and rewards. That's what we have to look at, right? So what are the states here? So the states are hot or cold, right? Hot means it's a hot selling product. Cold means it's a product that's not selling well, right? So the states are hot or cold. And what are the actions, right? There are 4 actions actually, if you think about it. I can advertise, not advertise, do research, don't do research. So there are 4 actions here, but only 2 actions are available at a time, right? So if you are in state hot, you can advertise or not advertise, right? If you are in state cold, you can research or not research. So these are the only 2 actions that are available in each of the states, even though totally you have 4 actions. So A of hot will be advertise or not advertise, A of cold will be research or not research, right? So that's basically what we have. A of hot is advertise or not advertise, A of cold is research or not research. Great. So now we have the states and the actions. So how do the transition probabilities and rewards work? So for that, let's try a simple pictorial representation. So I have 2 states, right? So what are the states? I have hot, I have cold. These are the 2 states that I have, right? Then I have in state hot, I can advertise or I can not advertise. So in hot, if I choose to advertise, what did we say? In hot, if we choose to advertise, we said with probability 0.8, you will continue to be hot. That means with probability 0.2, you will become cold, even though you are advertising, just the world, that's the way the world is, right? Some kind of a noise is there and then you become cold, right? And then you also get a reward of +4 whenever you advertise, regardless of whether you go to hot, whether you go to cold. The fact that you are hot to begin with, that gives you a reward of +4. Okay. Now if you choose to not advertise, right, with a probability 0.5, you still remain hot and you get a reward of +6, and with probability 0.5 you could become cold with a reward of +6. So if you think about it, so it's something like this, right? So probability of hot given hot comma advertise is 0.8. Then probability of cold given hot comma advertise is 0.2. Remember, this is P of S given, this is P of S prime given S comma A, right? So that's basically what we have. Then again we have P of hot given hot comma not advertise equal to 0.5. So that's what we have. And likewise, so the reward of hot comma A equal to +4. Right? So remember, we had S A S prime. Here I am saying regardless of what is S prime, the reward is the same. Therefore, this is how we write the reward. Right? Now, if you are in cold and if you research with probability 0.7, you go to hot, but you get a reward of -5. That means with probability 0.3, you stay in cold itself. Likewise, if you don't research with probability 0.6, you stay in cold, but you get a reward of -3. So this is the full MDP, right? So you can write down the transition probabilities like this, you can write down the rewards like this, and then you first think about the state from the word problem, right? You think about how you will form the, right? From the word problem, you think about how you form this states, right? How you form the states, how you form the actions in each state, and then how you actually come up with the transition probabilities in each of the states. Right? So that's basically what you look at. Right? This is how you formulate this MDP. Right? Like that, we'll give you several examples, both in the assignments and perhaps in the exams, for you to look at and how you form the MDP. Right? So these are 2 simple examples, right? One where you just had a grid-like structure, the other one where just had 2 states and 2 actions in each state, right? But then we talk about real examples, they can become very complicated. You can see this robot here, right? This robot has a lot of sensors and lot of actuators, right? So the inputs of the robot could consist of various sensors like bump sensors, right? These are bump sensors that tell you if you are hitting an obstacle, right? There are sonars, okay, that will emit some signal and then get back the echo and then tell you what distance there is an obstacle there. Here this bump sensors will tell you if you are actually bumping against an obstacle or not. And then you have a camera here, right? The camera will give you the visual input coming from the front, and then you have these things called wheel encoders that tell you how fast the robot is moving, like a speedometer, right? So they have something called wheel encoder that tell you how fast the robot is moving. And then of course you have sensors for looking at what are the different angles at which the arm is bent, right? So that sensors are also there, right? And then there could be potentially more sensors. There could be a GPS on board, right? And that's a Wi-Fi antenna. So you could be looking at Wi-Fi signals that are coming from various access points and so on and so forth, right? So all of these put together kind of is your set of sensors, right? And sometimes even with all these sensors, it might not constitute state, right? And you might need some history, right? So typically the state in such kind of robot control problems is a short history of all the sensor readings that are of interest. Okay, so it's actually not that trivial like we are talking about, right? And so we have to think about how this thing is going to look like, and some of this might require some discretization and so on and so forth. Right? The second thing that we have to think about is actions, right? So what are the actions here? So there are many motors. There are motors for the wheels here. There are motors for the arms. There are motors for the camera, like pan, right, tilt, zoom. So there are so many actions that you can have for the camera, for the motors and the wheels, as well as the joints in the arms, right? So all of these are various motors. Your actions could very well be a set of torques, right, that you give to all these motors. So there are 2 motors here, 2 motors here, and then 5 motors here, right? So 5 plus 2, 7 plus 2, 9 motors, and so this could just be a vector of 9 torques that you give to these motors, and that controls the system, right? Of course, there could be other ways of writing the actions, right? I've told you this already, right? There are many ways in which you can think of actions, but here is one simple way of thinking of the robot problem as a MDP. So finally, so you have to think about the rewards, right? You have the states, you have the actions, and then you have to think about the rewards. So rewards depend on what is the task that you are trying to reach, right? Suppose you have to go and grab a ball and give it to somebody, then you can give a positive reward of +5 when the ball is handed off to the target, right? But then what about along the way? You could have some negative rewards for bumping into obstacles, or you could have some negative rewards for just using up the battery on the robot, right? So the robot is running on some battery. So every time you move, you're using up some battery. So depending on how much battery you use up, you could get a negative reward. Or if you bump into an obstacle, you might get negative reward. Or you pick up an object and drop it, you might get a negative reward, and so on and so forth. And you get a positive reward on when you actually reach the goal. So this is how you set up the MDP, and of course the transition dynamics are a little tricky, so we'll have to think about that, or you can just run the robot and get data from that run and then use that to train the robot. So these are the possibilities.